Okay, so welcome back. Quick question. Someone said, "Is the homework ready for accuracy?" So, I mean, yeah, there's your TAs are gonna it matters. The answers you get on the homework definitely matter. So it's not just about completion. Um, so yes, the homeworks are graded for accuracy. Um, anyway, so yeah, as you all no doubt saw yesterday, I posted the homework, and I believe I posted all of the exercises from the different sections of the chapter that you need. So I'll continue to do that throughout the semester. I think that makes it easier for everybody. So anyway, um, as it as it goes from last time, we were finishing up our discussion of lines. Um, yeah, Mountain Dew sponsorship. That's definitely something. Actually, I have a funny story. Maybe after your first exam, I'll tell you a story about how my undergrad roommate and I spent like thousands of dollars on Mountain Dew when we were, well, at least the equivalent of thousands of dollars on Mountain Dew when we were undergrads. So anyway, that's a good story. We had so much Mountain Dew merch because they had some Mountain Dew promotion going on at the time that you got so many points from 2 liters and so many points from 12 packs. We actually accumulated enough points to get a ridiculous amount of Mountain Dew merchandise, so which I still have hanging in a closet. I at least have one of my Mountain Dew hoodie, my official Mountain Dew hoodies. Anyway, that's a story for another time. So I will just remind me to tell the story after your first exam. I will tell you all that story. So anyway, so last time we were discussing. Just a quick reminder, if I have line in space, picture looks something like this. So here's line. What do I need in order to be able to immediately write this thing down? So all I need is point on line. Call that P naught. So there's the coordinates of P naught. And I need a vector, big L, that is specifying a direction. It's basically a vector that is parallel to my line. Okay, and let's say that big L has components A, B, C. So A, I plus B, J plus C, K. Okay, so once I have those two pieces of info, I can immediately write both the parametric and symmetric equations for the line. So the parametric equations look like this. So x is equal to x naught plus at. Y is equal to y naught plus bt. And z is equal to z naught plus ct, and t is some real parameter. So that's where the name parametric equations come from. T is a real parameter that's parametrizing this line. We'll get more into that when we talk about curves in space, because this description is actually nice, because as we'll see, we can think of a line as being a curve in space. It's a really simple example of a curve in space. And as you'll see when we talk about this stuff in chapter 12, this way of thinking about it is going to lead naturally to describing curves. It's called a parametric description of a curve, so a parametric curve. You've actually already seen an example of this in the plane, but I'll save that for chapter 12 stuff that we'll start on Monday. So anyway, these are the parametric equations for the line. So these are parametric equations for L. The symmetric equations, assuming that none of these components of L are 0. If they are 0, then you can look at last lecture to see how to write the symmetric equations. So the symmetric equations for this are, all you do is you solve for t in each of these and then set them equal to each other. So this is x minus x naught over a is equal to y minus y naught over b, and I've run out of room here. So this is equal to z minus z naught over c. So in some instances, these can be really convenient to write. So maybe more practically speaking, the parametric equations are kind of better. But there's instances where the symmetric equations might be more convenient. So these are the symmetric equations for L. Okay, and of course you can go back and forth between these. There's no it's not like there's a line that can be written one way and not the other, so either of these are fine. Okay. And as we saw, so you can directly come up with these equations if you have point and vector that's parallel to line. But what if you have the classical thing that we know that determines a line, and that's 2 points, right? So here's a quick example. So find the, say, symmetric equations of the line containing the points -1, 1, 0, and I don't know, we'll say 1, 2, 3. Okay. All right. Okay. So we know, just coming from like basic geometry, this should be enough. This isn't the exact same info that I was given here, but this should be equivalent. I should be able to come up with this info from these 2 points. Well, what is this info I'm referring to? It's point on line and vector parallel to line. So I have 2 points on the line, so clearly I have point on line, that's fine. So now I need to come up with a vector that is parallel to this line. But to do that, all I do is just take the vector that starts at one of these points and goes to the other one, right? So if I call this point, say, P0, and I call this point P1, then the vector I seek is the vector with initial point P0, terminal point P1. Before you even ask, of course, I could have swapped these around. It doesn't matter. All that matters is the direction. When I say direction, of course, we mean the full line of direction. So if this were technically pointing in the exact opposite direction, that's also fine. Okay, so what is this vector? Well, it is a vector that has components that I get from just taking its terminal minus initial in each slot. Right, so terminal minus initial, so it's 1 minus 1i plus 2 minus 1j plus 3 minus 0k. Now, this is very simple, and we've done an example of this before, but I want to stress examples involving this because this is something that you're going to do over and over again in chapter 11 and 12, being able to come up with a vector between 2 points, right? This is the way to do it. So 1 minus minus 1 is 2, so this is 2i plus 1j, so that's plus j plus 3k. So this vector is parallel to the line in question. So I have a vector that's parallel to the line, and I can pick any point I want. Since we already labeled this P0, why don't we just pick this one? Oh, wait. Right? Oh, wait. How is this going to alter the symmetric equation? So again, x naught, y naught, z naught can be, it doesn't have to be exactly the same here, right? So what this means is that if you're checking your answers, just like I said last time, these equations could look different, right? They could look differently. They don't look exactly the same, but they're still describing the same line. So think about it when you have an equation for a line in space. So anyway, this would be x minus 1 over 2 is equal to y minus 1 over 1 is equal to z minus 0 over 3. And of course, you wouldn't leave them like that. You could simplify them a little bit, but that's all we care to do right now. Okay. Okay. So, one more thing I wanted to discuss about lines in space, and that's the distance formula for computing the distance from point to line. So, it's the wrong pin. So, distance from a point to a line. Right? And so, here's the following fact. So let L be a line in space parallel to a vector L, okay, and let P1 be any point not on the line L. Okay. Then the distance from P1 to L is given by the following. So this is, we'll call it D, or the distance from our point P1 to L. And this is given by the length of the vector L cross P naught P1 divided by the length of L. Okay, but wait, what's P naught? I didn't say what that is. Where P naught is any point on L. Okay. Now, this is a formula that purports to compute a distance. Okay, and of course, the quick warning, whenever you're dealing with distances, you can expect the answer to be bad, right? Well, you know, I mean, depends on what you mean by bad, but bad in the sense of typically you're going to have irrational numbers showing up, right? I mean, even right, the distance from one corner to the opposite corner of unit square is square root of 2, right? So it is unavoidable typically to talk about distance at all and not have bad numbers show up, but that's fine. Yeah, it doesn't mean done anything wrong here necessarily. So let's do a single example of this to give you an idea of how this goes. So maybe I'll move or I want this formula at the top of the page, so let's do this. Okay, so here's the example. So let's find the distance from the point 2, 1, minus 1 to the line with parametric equations. X is equal to 3t, y is equal to 1 plus 2t, and z is equal to minus 5 minus t. So there's my line, and here's the point. I want to compute the distance from this point to this line. Now, you might say, well, wait, doesn't this formula says that P1 is any point not on L? So if I'm given a point, do I have to check first that it's not on L? I mean, you could. That's an easy thing to check, right? But, does it actually matter? So let's think. Here, let's suppose that we screwed up and we actually wanted to compute the distance from a point that ended up being on the line L. Okay, then in this formula, if P naught is any point on L, then the vector from P naught to P1, right, is some vector that lies along the line. Necessarily, it would be parallel to big L. So then what would that mean for this cross product here? Right. Someone said, do I care if you all write vectors with square with the like corner brackets? No, that's fine. There's a reason I avoid that though, because in math that means something totally different. So that's some physics stuff. So if you're a dirty physicist, then I guess that's okay. But for us mathematicians, It becomes a zero vector. That's right. So Chad is saying that it becomes a zero vector. Big L is a vector that is parallel to the line in question. And so whenever you have two vectors that are parallel, their cross product is the zero vector. And so the length of the zero vector is zero, and so this distance is zero. So just to quickly recap, all I was saying here is that if it turns out that the point in question actually lies on the line, you don't have to check or anything because this formula takes care of it anyway, because the distance would be zero, right? So that length in the numerator would be zero, and nothing would matter from that. Okay, so then what do I need to do? So first of all, I already have my point not on L, and from this equation here, I can write what my big L is. So in this case, my big L, these come from the coefficients on the parameter t. Right, so big L is 3I plus 2J minus K. Right, that's just directly reading off this equation. So 3, 2, minus 1. And now what is the other thing I need? I need any point on L. And of course, I can pick any point, but why not just pick a very easy one where I've let t be 0? So our any point in this question would be the point 0, that's letting t be 0, 1 minus 5. Okay. All right. And if you want to, of course, you could pick a different point at this stage, work through this computation I'm about to do, and you'll see that you're going to get the exact same thing. Okay. All right. So now we have our point P1. That is our point not on the line. So to compute this distance, right, the distance from P1 to my line L is then this fraction. It's the length of L cross P naught P1 divided by the length of L. So I need to compute the length of L, and I need to compute this cross product of L cross P naught P1, and then the length of that thing. So first of all, what's P naught P1, this vector? So it's terminal minus initial in each slot. So this is 2 minus 0, so that's 2I. 1 minus 1, so that's 0j, right, plus 0j, and then lastly, minus 1 minus 5, so that's minus 1 plus 5, so plus 4k here. All right. Okay, and so now I want to compute the cross product. So what is L cross P naught P1? Well, let's quickly do this. So I have ijk in the first row here, and then I have L, which is 3, 2, minus 1, and then I have P naught P1, which is 2, 0, 4. So computing this cross product, this is something times I, that is 8 minus 0, right, minus something times j, which is 12 minus minus 2. So 12 minus minus 2. Okay, plus something times k, which is 0 minus 4. Okay, so simplifying this is 8i minus 14j minus 4k. All right. Okay. All right, so now I need to compute some lengths. So first of all, what is the length of L? Well, this is square root of 3 squared plus 2 squared plus minus 1 squared. So 9 plus 4 plus 1 is square root of 14 is the length of L. But then I also have to compute the length of L cross P naught P1. So what is this? This is square root of 8 squared plus minus 14 squared plus minus 4 squared. So this is square root of 64 plus, what is 14 squared? Oh, I don't even, what is that? Like, let's see, that's like 140 plus 56, so what, 196, right? Okay, plus 16. Okay. And so, this is 64 plus 196, so this is 276 is what I get here. So this is square root of 276 divided by the square root of 14. This is 2 times 7, this is 2 times 138, so this is square root of 138 over square root of 7. If you'd left it like this, that would have been fine. Okay. All right. Okay. So that is how that goes. All right. So if you have any questions about that stuff, you can put them in the chat and I'll answer them here in a bit. But now we want to talk about planes. Okay. So this is the last thing that we're going to talk about in chapter 11. So this is 11.6. What we were just doing, lines in space, is 11.5. And all the other stuff is kind of combined before that. Really, after we got the basic stuff defined, it kind of starts in 11.3. Okay, so what do I mean when I talk about a plane in space? So previously, of course, I gave this example that a plane in space, it is kind of the analogous object geometrically to a line in the plane, right? Because a line in space doesn't separate space like a line in the plane does, right? So a line in the plane separates the plane, but a line in space doesn't. You can go around it. But a plane in space has that same separation property, right? And so as we'll see, kind of, I'll go ahead and spoil some of the fun here. Just like in Calc 1, right, the main application, kind of the original thing that we were interested in doing when we were talking about analyzing a curve, was being able to write down the equation for a line that was tangent to the curve at some given point, right? So that was literally like the entire purpose of Calc 1, basically, was doing this. That was why the derivative existed, was to allow us to do that. Okay, so in Calc 3, being the multivariable version of Calc 1, you're going to see that the graphs of functions we're going to talk about are now not curves like they were in Calc 1, but they're going to be surfaces. Okay, and so when it comes to discussing surfaces, it's no longer really the proper notion to talk about tangent lines to a surface. Because as we'll see, it's not well defined. There's too many tangent lines to a surface. And so what becomes the key concept is the notion of a tangent plane to a surface. Okay, and the tangent plane to the graph of a function of two variables in space is going to be the analog of the tangent line to the graph of a function of a single variable in Calc 1. Okay, so planes are important for that reason. Now, what do I need in order to describe a plane? So this is a question kind of purely conceptually. This is not necessarily something that you'll have seen before anywhere. Oh man, that is horrible. That's bad. Forget that I did that. Okay. So, I have plane here. Okay. And let's say, of course, I have a point P0 in my plane. Now, clearly, I'm going to need more info than just a point. If I ask you, what is the plane that passes through this point, right? You're immediately going to tell me, well, I mean, there's plenty of planes that pass through a given point. So you're going to need more info than that, okay? And so, same notation. We'll say that our P0 has coordinates x0, y0, z0. And we want to describe a generic point P, okay, that lies on this plane. And of course, maybe P is here, maybe P is over here, maybe P is over there. The idea is that I have some generic point P, and I want to describe the plane. I want to come up with an equation that says this plane in space is the set of all points x, y, z, such that blah, right? And that's going to describe my plane. So what thing do I need here, right? So to describe a line, I needed a point on the line and a vector parallel to it. Here you can see that a vector parallel is not going to do me any good. That's going to give me a line, but not a plane. So what is the thing that I need? It turns out, and some of you might have, hold on, I had my screen minimized, so maybe someone even said it. Nope, doesn't seem like anyone said it yet, so I'll go ahead and say it now. What you need is a vector n called the normal vector to the plane. Okay, what is the normal vector? What is its key defining property? It is perpendicular to any vector that lies in the plane. So n is the normal vector to the plane. I haven't named my plane yet, so maybe I should do that. Let's name my plane script P, or if you're using LaTeX to write it, maybe mathcal P. All right, so n is the normal vector to the plane P, i.e. n is perpendicular or orthogonal to any vector that lies in the plane P. Okay. Okay, let's go ahead and give ourselves some notation here. This vector n, we'll say that this is ai plus bj plus ck, right? All right. So you have a couple of questions before I write down anything else. One, I said n is the normal vector, implying there's only like one. Okay, that's a little bit misleading. Okay, it's a little bit misleading because you might say, well, this normal vector is here, but could you have a normal vector for this plane, say, based over here? Right? Is that okay? Is that the same vector? Yeah, we know that's the same vector, so that doesn't confuse us, right? So that's okay. All right. But what if you had a vector that looked like this? Right? Or what if you had a vector that looked like this? Are those two vectors, the last two that I just drew, are those also normal vectors for this plane? Yes, they are. Okay. They are. Okay. So both of these vectors I just drew are also normal vectors, because the key defining thing of the normal vector is it's a vector that is orthogonal or perpendicular to any vector that lies in the plane. That's true for both of these vectors. Okay. And so a normal vector is not unique. Okay, so this is a little questionable for me to write this here. So as it turns out, normal vectors, yeah, I'll just write it out instead of saying that. So normal vectors are only unique up to scalar multiplication. Now this is a fancy way of saying that what is the relationship between any of these vectors I drew here that are normal vectors for this plane? Well, the relationship is that they're parallel, right? So if you have a normal vector to a plane, any other normal vector to it is parallel to that vector. Okay. Conversely, if you have a normal vector to a plane, okay, and you have another vector that is parallel to it, then that is also a normal vector to the plane. Okay, so it works in both ways. All right. Okay, so now that we've written this, we can really write out the thing that determines what's going on here. So the main fact here, before this gets lost, is that my normal vector is perpendicular to any vector that lies in my plane. So I have a point, P naught, that the plane contains, a normal vector to the plane, and some generic point P, I can draw this vector P naught P, right? Well, what is the vector P naught P? Well, P has coordinates x, y, z. P naught has coordinates x naught, y naught, z naught. Again, you're seeing this over and over again. If I want to write this thing out, what are its components? It's just terminal minus initial in each slot. So this is x minus x naught I plus y minus y naught j plus z minus z naught k. Okay, so there's P naught P. Now I want to take this starred statement and translate it. If this thing is perpendicular to any vector that lies in script P, well, then it's perpendicular to this one, because this is just some vector that lies in my plane. And so, what does it mean if I have a vector that is perpendicular to some other vector? It means that their dot product is 0. That's what it means. This is the equation for a plane in space. Okay. Well, this isn't that practical for us because we want it in the actual coordinates because we're going to be computing with this. So this is nice, and this is exactly where this comes from. But I want to actually see what this means, right? And so if P naught P has components x minus x naught, y minus y naught, and z minus z naught, and N has components A, B, and C, well, let's actually do this dot product, right? So that's what I'm going to do on the next page. So I have N, no, that's not it. I have N dotted with the vector P naught P is equal to 0. But again, just to remind you, N is ABC, and P naught P is x minus x naught, y minus y naught, and z minus z naught. And so what is this? This is A times x minus x naught plus B times y minus y naught plus C times z minus z naught is equal to 0. This is the equation for a plane. So this is our equation for the plane script P containing the point x naught, y naught, z naught, and having AI plus BJ plus CK as its normal vector. Okay. An equivalent form here. Imagine you distributed each of these, so A times x minus x naught, B times y minus y naught, C minus times z minus z naught, and then you moved all the stuff that came from that multiplication over to the other side. So plus ax naught plus by naught plus z naught is what you have on the other side. You could also rewrite this equation as ax plus by plus cz is equal to d. Okay, this is an equivalent thing, so both of these things are the same. Okay. What is, of course, nice about this one is you can immediately read off a point, right, if you like here. But of course, it doesn't matter. These are equivalent. Okay. So a couple of things. One, you can notice immediately, right here, that of course you're allowed to scale your normal vector any way you want to. Take a normal vector, multiply it by 5, right? So then instead of having ABC, you would have 5A, 5B, and 5C here, which in this equation would amount to having 5A times x minus x naught plus 5B times y minus y naught plus 5C times z minus z naught. Of course, you can divide through by 5 and you get the exact same equation. So this explains the algebraic reason why geometrically a normal vector is only defined up to scalar multiplication, right? Okay, so that's the idea here. All right, and so I want to say a couple of things here. One, you might find it a little weird conceptually that what info did we need to write out a line? Well, we needed a point, right, that was on the line, and a vector parallel to the line. Okay. What info do we need to describe a plane? Well, a point and a vector, right? A point that's on the plane and a vector that's perpendicular to the plane. It seems a little weird, right, that it is the exact same info, right? Forgetting the relationships that those vectors have with the object, it's the same amount of info. It's a point and a vector, right? But in one case, we get a line out of it. In the other case, we get a plane. So it seems a little strange that, it seems like you're getting a lot more info in the case of a plane somehow. And the reason for that is because that orthogonality relation encodes a lot of what's going on there. It is somehow a higher dimensional piece of data that you have. Okay? And so, of course, what's nice is if you have the equation of a plane, then you can just read off stuff from it. So here's an example. So find me 3 points on the plane 5x minus y plus 7z is equal to 2, or let's say is equal to, let's do is equal to 0. So find me 3 points on this plane, and also a vector normal to it. Okay. So find me 3 points on this plane. Now, we have a lot of options here. Well, what about the point? Well, you might say the origin works. All right, this is our first point. Why does the origin work? Well, I just plug this in, and it's fine, right? So if I plug in 0, 0, 0, I get 0 is equal to 0, so that's on the plane. Okay. What's another one? Well, if I have x is equal to 1 here, that would be 5. But then if I had y is equal to 5, I would have 5 minus 5. That'd be 0. And then I could set z equal to 0. Right? And so another point would be 1, 5, 0. Okay. Well, what about a third point? Well, again, if z is 1, that's 7 here. Y could be 7 to cancel that out, and then x could be 0. So 0, 7, 1 is another point that is on the plane. Okay, so I intentionally picked this equation to be, not too simple, so that you had to think about a little bit, how you would come up with these points. This is an example of how to come up with 3 points on a plane from that equation. Of course, we could come up with way more than 3 points, but we're just going to stop at 3. That's what I asked here. Okay. So question, don't we need 2 points for a plane? P0 and P1? No. So the only points you need for a plane is you need a single point that the plane contains, and then you need a vector that is normal to the plane. Because that is all the geometric info that you actually need to describe that entire two-dimensional space. And it's because you're using the relationship of orthogonality or things being perpendicular. Okay, this gives you a lot more geometric data than you might think. Okay, and I want to find a vector normal to it. That's easy. So I can just read that off from the coefficient. So 5i minus j plus 7k, right? All right. So this is normal to the plane. All right. Okay, so let's do it in another way. So here's a more straightforward thing. This is just the definition, right? So write the equation for a plane containing the point 0, -1, 4, and having the vector, we'll say 3i minus 2j minus 4k as its normal vector. Well, just from the definition, and if I bring that back, this is my equation for the plane, okay, or similarly this, however I want to write it. I'm just going to write it like this. And so this is just 3 times x minus 0 plus minus 2 times y minus minus 1, right, plus minus 4 times z minus 4 is equal to 0. So if I simplify this a little bit, of course, this is 3. And I'm going to leave it like x minus 0 so that you can see the point in question. Minus 2 times y plus 1 minus 4 times z minus 4. Okay. So you can exactly see the point that we started with as our point that the plane contained, and this as its normal vector, the coefficients on x, y, and z. Okay. All right. Geometrically, though, what was the way that we determined a plane in, say, like Euclidean geometry, right? So just like there was a postulate for 2 points determining a line, how many points do I need to determine a plane? 2 points are not enough. 2 points determine a line, but they're not going to tell you. If I give you 2 points and say, find the plane that passes through those 2 points, that's not enough, right? It's not enough info. So what about finding the plane, so there's multiple planes, right, that pass through 2 points. So me just specifying 2 points and asking for the plane that contains them, there's infinitely many answers. 4 points will work, but it's too much. Okay, so 3 points is the answer. So fact from geometry, 3 points determine a plane. Now, this is not quite correct, right, as written. So can someone tell me what can go wrong with 3 points? If I just give you any 3 points, is there any scenario that could happen that could make it so that those 3 points would not determine a plane? Someone said it in chat. Unless they fall on the same line. If they're collinear, it's no good, right? So 3 points determine a plane. What we want here is 3 non-collinear points determine a plane. This is, again, the notion of being in general position for those points. Okay, so those 3 points can't lie on the same line. Okay, so those 3 points can't lie on the same line. If they do, then you don't get a plane. You, again, just get a line. All right, and so what that means is that I should be able to come up with the equation for a plane from 3 points. So here's a quick example. Find the equation for the plane containing the points. Well, let me make sure that they're actually collinear, or not collinear. So yeah, let's pick points. P naught we'll say is 1, 0, 2. P1 is minus 1, 3, 4. And P2 is 3, 5, 7. Yeah, these are not collinear. Now, do you have to check? The answer is no. It'll be clear from the process that this has gone wrong, okay, and you'll see why. How do I do this? All right. So, supposing that these are not collinear, what do they look like? Pretend that the plane in question is this sheet. And yeah, the sheet that, as you know, you're looking at it right now is laying, flat. It's laying horizontal. But say that it's like this, right? And I just move my camera so that it looks like it's flat, right? The camera's field of view is perpendicular, right, to this thing. Okay, and so imagine the sheet of paper is the plane. So if these actually determine a plane, maybe they look like this, okay? So I'm not going to actually pay attention to where these things are oriented, but just conceptually, there's my 3 points, P0, P1, P2 in the plane. Again, not paying attention to actually any of the coordinates there. Okay, so here's my 3 points in the plane. How do I come up, from these 3 points, how do I come up with the amount of info that I need? What do I need, right? I need a point in the plane. Well, I've got 3, so I got plenty of choices there. That's fine. What else do I need? So I need a point in the plane, and I need a vector that is perpendicular to the plane in question. How do I concoct a perpendicular vector to the plane containing those 3 points? Well, from these 3 points, I can come up with 2 vectors. And these vectors are not parallel so long as these points are not collinear. There they are. All right, so here's the vector P0, P1. And here's the vector P0, P2. What is a vector? Someone tell me in chat. What is a vector that is perpendicular to those 2 vectors? Well, you know what it looks like. Looks like that. Or it looks like the vector that goes into the paper, right? And so, what is that vector? Cross product of those 2, right, exactly. And so note, the vector that is formed from crossing these 2 vectors right, is perpendicular to the plane in question. Okay. And so all we do, since there's only a couple minutes here, I'm gonna skip ahead, but this is what you would do. So you would write out P0, P1, P0, P2, cross them to get the normal. So exercise for you all. This is ungraded, but you should do it. So finish this. All right, so find the equation for this plane. Okay, one more thing that can be done, and we'll do this maybe at the beginning of class next time, and then we'll be done with our discussion of planes, is the following. So if 2 planes, script P1 and script P2, intersect, what geometric object results from this intersection? So what geometric object results from the intersection of 2 planes? And you can tell me in chat, so think about it for a second, right? So a plane continues indefinitely in all directions, right? So you have 2 planes continuing indefinitely in all directions. There are 2 possibilities, right? So the planes either intersect or they don't. If they do intersect, exactly, they intersect in a line, right? A line. And so 2 planes that intersect in a line of intersection. So one of the main things that we'll do, kind of a really great thing to tie together everything in chapter 11, is to find an equation for a line of intersection for 2 planes. Okay, so we'll do that at the beginning of class next time because it's a good thing to do. Another thing is if 2 planes do not intersect. So 2 planes, P1 and P2, do not intersect. I.e. they're parallel. Is there any way to detect this from their equations? So you have two planes. So there's corresponding equations for both of those planes. And let's suppose that the two planes do not intersect. Okay. All right. Well, if they don't intersect, how would we know? Right, someone already said it. It's that their normal vectors are parallel. Right? So in this case, their normal vectors are parallel. Okay, and so their normal vectors are parallel, meaning that they're scalar multiples of each other. So you could immediately detect it from the equations or from just having their normal vectors in front of you. Right? Again, you could cross their normal vectors to check whether or not they're parallel, but you don't need to do that, and you shouldn't do that if all you're doing is checking that they're parallel. Okay, if you have two normal vectors and you just look at them, you can see whether they're scalar multiples of each other. So if they are, in fact, scalar multiples of each other, then the two planes in question are parallel. They don't intersect. That's right. Okay, so that's most of the conceptual geometric stuff out of the way. I'm going to do one example on Monday of finding the line of intersection, or the equation for the line of intersection of two planes. After I do that example, I will talk about the distance from a point to a plane, which is really quick, and then we will start on Chapter 12 stuff. So Monday we'll start on Chapter 12 stuff. We'll finish all the Chapter 11 stuff. So your homework covers all of Chapter 11. Your next homework will cover all of Chapter 12. So that is how it goes. And then your first exam, I will post when your first exam is going to be. I'll look at the lecture schedule and see when's a good time to have it. So your first exam will be sometime after we finish. It'll be like the day after we finish Chapter 12 or the day that we finish Chapter 12. Chapter 12 so your first exam, covers Chapters 11 and 12. And then that'll be that. So it'll take us at least 4 or 5 lectures to cover Chapter 12. So your exam is at least a week and a half, 2 weeks away. All right. So anyway, I will see you all on Monday. What sections were covered today? We finished 11.5 and covered 11.6. Okay. Maybe I'll write that in chat so that everybody sees it. Okay. Yeah, actually what I'll do, Javier, is I will just annotate the videos so that I will add the sections covered to the video. So I have descriptions. I have like a little video description on all of them. I'll just add in parentheses the section numbers rather than just the things that are covered. That's what I'll do. That way you can just see it. I'll also organize this into a playlist. I'll do that over the weekend. So this is the 6th video in the playlist. So anyway, also next week I'll talk about maybe holding some office hours for an hour next week, and I'll let you know when that's going to be. But anyway, I will see you all on Monday. So have a good weekend.